All right, last activity for the lesson. This is our work on how particles behave in different states of matter. So I'm on pages 5 and 6 of your booklet, and you'll notice on the right-hand side of the screen I have the PhET simulation States of Matter Basics open. You can find that on your topics page, just underneath the thing link where you're watching these videos. So, the first task is for you to explore solid, liquid, and gas for neon. I chose neon because it's a noble gas, so it has simple single atom structure, and you can easily see what's going on. So on the PhET, you simply press solid, liquid, gas. Look about how they're arranged, also look at how they're moving. And then I'd like you to have a go at the questions A and B on page 5. Question A is to draw diagrams. Please don't try to draw all 30 or however many atoms are in the simulation. You can do 6. That's plenty. And for part B, you're ticking solid, liquid, or gas, or sometimes more than one, for these statements. Okay, so pause the video now and have a go at those two activities. Right. Hopefully you paused and you did these. And now we can go through the answers. So for solid, you'll notice in the simulation they're in nice, neat rows, and they are touching. They are still moving. Common misconception is that solid particles are still. They're not. They're just stuck in place and vibrating on the spot. So to draw that, put them in a nice, neat row, and put another row underneath. And that's it. You're done. In the simulation, some of you might have looked really carefully and realized their rows are kind of staggered. Absolutely fine. Both of those would be perfectly acceptable drawings of a solid. I'm going to skip to gas now. Gas is one that most students find really easy. Gas particles are all separated, very far apart from each other, moving quickly. Which leaves us with the middle one. Everybody wants liquid to look like some kind of merging of solid and gas, but that's not it. So people will draw this. They'll draw them kind of medium distance apart. That's wrong. Okay? It's not a halfway point between solid and gas. It's its own thing. Liquid particles are still touching, just like they were in the solid. The difference is they're no longer in neat rows. So you need to be really cognizant that you're drawing them randomly. And I have some gaps, that's great, but they're all touching. That's important. If you're not touching, you're going to lose a mark. All right, let's go through these statements. The particles have the most energy in this state. So that's going to be the one where they're moving the fastest. If I look at the simulation, that's clearly the gas. Vibrate on the spot. Solid is the only one where they're just vibrating back and forth and back and forth. So that's solid. Particles are arranged far apart. Gas. Randomly. Gas. And also liquid. Remember, we had to draw them without the neat rows. The forces between the particles are strongest means they're held together really tightly. And that's the solid. That's the one where they're held together the tightest. Liquid would be the next tightest. And then gas, there's no forces between them at all. They're completely separate. So the strongest is solid. Particles can flow. Okay, everybody likes that for liquid. We know liquid particles flow over each other. Gas particles flow too. You saw that in my demonstration of the hydrogen peroxide chemical reaction. The oxygen flowed up and out of the flask. Both liquids and gases are fluids. Both of them can flow. The particles move quickly past one another. I don't like the way I've worded that. Moving past one another sounds like liquid, but the way it says quickly would lead you to think it's gas. So I will accept either of those for that one. Okay. Neat rows is clearly solid, close together solid, and liquid. That's the common error students make. They forget the liquid are close together. And least energy is the solid. They're moving the slowest. Okay, sorry about that. Right, so the second half of this activity is about changes of state. And we're going to start with the difference between two that you're probably familiar with, the change from liquid to gas. And That can be called evaporation or boiling, depending on what temperature it's at. If it is at the boiling point, for water that would be 100 degrees C, then boiling occurs. That is when all the particles have enough energy to change from a liquid to a gas, and they all escape the sample at once. If you boil water in the kettle, you get bubbles from the bottom, on the side, and then all of the water is able to change to a vapor. If you open the PhET simulation in a moment and increase that temperature way up, you'll see the whole sample boil. Evaporation is slightly different. This is below the boiling point, and it's a slow process. So for example, if I spill a bit of water on my desk today and I go home, when I come back tomorrow, the puddle's probably going to be gone. But I think we can all agree sometime in the middle of the night, it didn't start boiling and bubbling and reaching 100 degrees. Something else happened. Evaporation is when the particles that are moving the fastest, so they're all bumping around in liquid, some moving a bit slower, some moving a bit faster. The fastest ones that have enough energy escape from the surface. Because they're on the surface, they're not touching as many particles as the ones in the interior, so they're not held quite as tightly, and some of them can escape one at a time, slowly, until eventually the whole puddle is gone. That's the difference between evaporation and boiling. And if you play the PhET, if you play along with the PhET, you might be able to see it, where one little particle will escape from the bunch and be flying around the top. So if you want to pause now, you can have a play with the PhET simulation, see if you can see the difference, and then come back and we'll go through the answers. Right, hopefully you paused, and now you're ready to check. Changing from a liquid to a gas is both of these. At the boiling point is boiling, below is evaporating. The surface is evaporation, whereas the whole liquid is boiling. And finally, only the highest energy particles, that's boiling, that's evaporation. All the particles, that's boiling. Okay, so that's the difference between the two. Finally, page 6, we're going to explore the rest of the types of changes of state. So I'm going to start with some notes on the bottom. Some of these you know already. Let's do the ones we just did. Liquid to gas is boiling or evaporation, depending on the temperature. Okay. The reverse, when you have water, like in Bermuda, when you have a lot of water gas in the air, it's very humid. If you take something cold out of the fridge, you get condensation on it. That's the gaseous water becoming a liquid. So that process is called condensing. Two others you'll be familiar with are these two down here. If you take solid water, ice, and it turns into liquid water, that's called melting. And if you take a liquid and try to turn it back into a solid, you have to freeze it. Freezing. Those four are pretty common terms. You've probably heard of them before. This one across the top, however, is new to a lot of students. Some substances aren't liquid under normal atmospheric pressure. So if they start as a solid and you heat them up, they skip straight to gas. That process is called sublimation or subliming. And a good example for subliming is dry ice. You might have heard of that or seen it if you've ever, they probably keep vaccines on dry ice if they want to keep them cold. Dry ice is solid carbon dioxide. And all it does is fume. It turns into a gas and then it disappears because it's become carbon dioxide gas. It doesn't ever turn into carbon dioxide liquid. Right. So, what kind of questions will you be asked about these? Oftentimes, you're asked to write equations for these changes of state. And they're really the simplest equations you're ever going to write. The substance stays the same. So for example, for our boiling water, it's still H2O. The only thing you have to change is the state. We use S for solid, L for liquid, G for gas. Now I'm going to have to help you with the formulas, so I'm just going to walk you through this one. I don't recommend you pause the video necessarily. Just try to follow along. So the first one is neon. If you look on the periodic table, neon is Ne. So I'm just going to write Ne on both sides and then work out what change of state it was. So condensing, you look down at the bottom of your page, That's from gas, G, to liquid. Argon on your periodic table is Ar. And freezing is the change of state from liquid to solid. Oxygen is an interesting one. It's O, but if you remember from the previous activity today, we saw that oxygen is diatomic. It goes around in pairs. So you actually need to write O2. There are 7 of them you will have to memorize eventually, but not yet. Evaporation, liquid to gas. Okay, next one, nitrogen is just like oxygen. It needs a 2. And that's boiling. Boiling is the same as evaporating, just at a different temperature. So boiling is also liquid to gas. Last but not least, melting ice. Ice is just H2O. And if you melt it, you change it from a solid to a liquid. All right. Question 4 I've kind of already answered. Some substances don't exist as liquids but convert straight from solid to gas. We said that was called sublimation. And an example of a substance that does that is carbon dioxide, otherwise known as dry ice when it's a solid. And last but not least, if you finished the lesson a bit early and want to have some fun, go back to that PhET, click on changes of state, and see if you can figure out all the different ways you can make a container explode.